Hello, I'm Curtis Hammerl, and I'm here to present dAuth, Federated and Resilient Cellular Network Authentication. This work was led by Matthew Johnson, who was in my lab but moved on to Starlink, and so his advisor is having to give the talk. So this research focuses on a relatively underexplored population, at least in the SIGCOMM and networking venues, which is the middle part of this. So on the left, you see the 5.4 billion people who are successfully online. This is a bit overstated, but we're using the ITU numbers. And on the right, you see the 160 million people who are completely off of the network, a normal focus area for our research. This focuses on connecting people who are within coverage, but not using the network. There's myriad reasons for this, primarily financial, people who simply don't have the money to pay for internet access, but other things like content, language, and other barriers to keep people offline exist. Now, the core thesis here is that people without connectivity are people who existing deployment models, that being AT&T, $100 a month plan, iPhone, all that kind of stuff, don't work for. Somewhat tautological. But to address these populations, which are often unhoused or immigrants and the like, you're going to need different methods to get access to them and to get them online. And so what we do is we work on a thing at a space called community networks. Community networks are networks owned and operated by the kind of community organizations that work with these populations. And these fundamentally change the dynamics of access in a number of meaningful ways. On the economic side, they're much cheaper. They're able to use local actors, local space, get access to a roof for free, that kind of stuff. They're also able to build local capacity, train up engineers to do maintenance instead of paying a high-class telecom engineer to come in. But on top of that, they also have capabilities that traditional networks don't have, which could involve designing the network for these specific populations, saying if you're going to work with the unhoused, build a network that really targets them from the infrastructure side. And this allows you to do outreach to those communities equally well. So we have a bunch of example projects in this space. On the left, far left, you can see my initial thesis work in Indonesia, which was one of the first community cellular networks. Middle right, you can see the Seattle Community Network, which you're going to hear about. Next to that is the Tribal Broadband Boot Camps, which the SEN lead, Esther Jang, has worked with for a while, helping Indigenous tribes in the US build out their own infrastructure. And on the far right is one of our test networks in Ulukhtuk, where Spencer Sevilla is on a roof turning a wrench, which is something we do a lot of in our networks. Now, concurrent to all of this, the sort of long thread of community network work, actually traditional telecom models are starting to approach these as well. A big motion that's been going on is a thing called private cellular. Now, these are basically identical to what we're talking about. Hey, we're going to let networks be built by small organizations that have their own needs. Now, they're not going to be targeting social organizations, right? They're going to be targeting other businesses. And indeed, the primary driving use case for private cellular is, at least in the sort of business literature at the moment, are factory use cases. You can imagine saying, hey, we have really precise automation needs. Wi-Fi is insufficient for that. Let's deploy a cell phone network instead. Grandview Research, an industrial research firm we cite because they agree with us, expects compound annual growth of the space of 51% through 2023. So there's both social and non-social sort of forces pushing us in this small private network direction. And this is because there's been a bunch of technological innovations supporting this. The big one is spectrum. CBRS provides high quality 3.5 gigahertz cellular quality spectrum to kind of anyone who wants it. And indeed, our experience, despite being in Seattle, a dense urban area next to some of the largest naval deployments out there, we see ready spectrum available in CBRS bands. So that's been great to us. But concurrently, a lot of telecoms have actually been taking the lessons from SIGCOMM in the networking community to heart and begun using cloud technologies. So this is a commoditization of hardware, including radios as well as servers, and the importation of open source tools, specifically Open5GS, which is an open source core network solution that we use in our project that you'll hear a little bit more about. So with this whole thread, we decided to start to build these kind of networks, and specifically in the Seattle Community Network. So the Seattle Community Network is a low-cost or free access network deployed throughout the Puget Sound region. Our goal is to provide access to people who can't pay for networks, can't afford user devices, or maybe don't know how to use user devices. Seattle Community Network has 7 cell sites all throughout the region, starting up in Seattle down to Tacoma. And these are the kind of partners that we work with: community centers, high schools, libraries, hacker spaces. Not telecoms, but these sort of socially minded organizations that we care about. Notably, the Seattle Community Network also runs Wi-Fi sites with a series of tiny home villages for the unhoused throughout the region as well. Hopefully, you'll hear more about that in a future SIGCOMM work. Now, with this model of access in mind, I'm going to describe the kind of vision we have for what we want this network to be, which is a thing we call cooperative cellular. So on the top, you can see a traditional telecom, and you can imagine red is T-Mobile and green is AT&T, right? And they compete over coverage. Customers will come in and say, hey, for this price, I get better coverage at my house or whatever like that. Now, when we're working with all these kind of smaller organizations, what we want to do is build something that we call cooperative cellular. The idea here is that each one of these is one of these small NGOs that we work with, and they don't want to compete, right? They just provide coverage to the communities that they work with, and we want them to be woven together to provide connectivity and provide sort of the vision of one large telecom. And we do this through roaming. In a traditional network, again, if you're an AT&T customer, you're not going to roam onto T-Mobile. Those are competitors. They don't have those agreements in place. In our network, these are cooperating organizations. And so absolutely, if you're a Blue Network subscriber, that's a cultural center, you're happy to roam onto the high school network. That's fine. Now, with this vision, which we think is great, we notice one small problem, which is these are not telecom grade installations. Essentially, these are small organizations that don't really want to be ISPs and don't have a large technical background behind them. They want to connect to the communities. They understand how important the internet is, but they don't have the capacity to do more than that. And so there's going to be outages. What we saw is nothing at 3 nines of availability in our network. And so the goal of this project is to design a roaming protocol, which is resilient to the kind of transient failures that we see in the Seattle Community Network. We found 3 key properties of what we wanted to build in this solution that we call dAuth. The first is to be able to tolerate failures. And this is, as mentioned, just the kind of failures we see in our network. The second one is that this is an open network federation. We want people to be able to join the federation, but we won't necessarily trust all of them. We don't know all of them that deeply, and that's going to be something we're going to have to resolve. And then lastly, we have to be backwards compatible. We can't go to Nokia and expect them to build us special radios or special phones. We need to handle the economies of scale that are already present. So I'm going to start with a brief background in authentication. So the first thing to note is that in a cellular network, there is a symmetric key shared between the authentication server, which is in the core network, and the mobile phone, which is in the SIM card. So this is actually a symmetric key that's copied and shared on both sides and used for encryption. Then a bunch of messages get sent back and forth, and a session key gets derived, and none of this is super exciting. But an interesting point, which we're going to leverage, is the fact that the session key itself is not actually sent over the wire, which is different than, obviously, internet communications. Instead, it's just generated from the data on both sides and then used. So the challenges for this federation are that the cellular roaming does work, right? Like right now you can roam onto another network. We roam all the time when we travel, but it's not going to work for us because it requires that the home network be online, the traditional roaming, and that's not going to be the case for us. And the symmetric key could be shared. So the easiest sort of simplest version of this is to simply replicate the symmetric key onto all networks, but that's horrifically insecure. People could hijack your account, hijack your identity, a whole bunch of stuff, and so we don't do it that way. So now what do we do? Well, we take 2 building blocks. The first is proof of presence. It turns out the home network can pre-compute the expected result from the auth token that they send out, so the expected result from the UE ahead of time. And so what we do is we actually hash that and share that to intermediate networks and intermediate backup networks so that they can validate that the user exists. This allows us to know, without sharing the private key, that the user is who they think that this token was generated for. Secondly, we use threshold secret shares. This is an established primitive in multi-party cryptography, which basically allows a key to be divided into n parts, and then m, where m is less than or equal to n, of those are needed to be able to reconstruct the key for its use. And so this allows us to split this session key up among multiple backup nodes and balance that against the security properties that we might want. It's a sort of a variable they can take into account as to how secure, how many backups they need to trust in order to be able to accept this user. So those were words. We're going to separate the auth from the key. We're going to do a proof of presence with multiple parties to get that final session key. And this will all generate verifiable data back to send to the home network for record keeping purposes. Okay, so again, this is all words. What does this look like in a more understandable form? So first on the left, you see the serving network. This is the one that's basically the one that's being roamed through, and it's blue. On the right, you see the green network. This is the home network who holds the symmetric key for the green user who's going to be attaching to the blue network. And then between are all these backup networks. These are other networks in our federation who are going to be serving as a way for a user to authenticate without going back to the home network. And these backup networks are pre-distributed with an auth tuple, a hash of the result, the expected result from the UE, and a session key share. So those components that we talked about previously. When the green phone shows up on the blue network looks up that user in a distributed, or that user's network in a distributed directory. And this gives them the backup networks as well as the home network. Then they talk to the home network, and if the home network's there, authenticate them as normal. We can do normal roaming if that network is available, which is hopefully still a majority of the time. Now, if they're not available, what we do instead is that the serving network, the blue network, requests the auth tuple from a single backup signed. So again, the backup they got from the directory. The backup validates that user to say, or that serving network to say that's a valid serving network that we trust, and then returns the authentication and the hash of the expected result. The authentication is presented to the UE, and then the UE replies with the actual result. So again, validating that the UE who they say they are. The serving network then presents the hash of the result to all the backups that are set up in the distributed directory. The backups store the signed key request to share with the home network later, and then validate the serving network's reputation again. So all these networks say, okay, this is a good player. We're happy for them to serve this user. The backups provide the key shares, which are given to the serving network, who can put them together to make the session key, and the communication can go on. Later on, once the home network recovers, the backups can provide those auth proofs to get to that network so that they know that the user has gotten traffic or gotten network access, and they get new refreshed key material for the next time that this happens. As long as n minus the threshold, which is a variable we get to choose, backups are honest and online, the user is protected from attaching to a network of insufficient reputation, so one that they trust and that their home network trusts, and auth results are returned to the home network so that they can make future decisions about who to trust, and potentially bill the user if necessary. Now, an important point to make here is that as a federation, this scales differently than traditional roaming. The only centralized information, aside from that key in the home directory authentication center, is the backups and the home network stuff that goes into this distributed directory, which is relatively infrequently changed. So basically easy to scale and similar to DNS in thought. An important point to make as well is that different networks can have different sets of backups. These are all configurations they can make. The green network here selects these, for instance, the blue network selects these, and the red network selects these. And it can choose those both for security and performance reasons. You might pick a set of networks near you geographically in order to improve the amount of communication or the latency of the communication in this authentication scheme. So this leads to natural load balancing behavior across the many organizations, which is actually really critical for us because a lot of the organizations we work with are relatively small and want low-end hardware for their installations. Many details are left out here. Please read the paper. You're happy to talk to me and maybe even Matt, who's going to have it in much more deep thought than I have. So how do we evaluate the system? So first, we implemented a prototype integrated with Open5GS, which is the core network used by SCN and other networks like us. To test scalability, we use a simulated RAN. This is UE RAN sim to be able to simulate hundreds of phones, and this really looks like a normal network. First, we began with a real-world evaluation with a real-world eNode B and a real-world phone, and it just works. So as a point, like, that part's good. And then we did the simulated RAN. In this, we did 12 auth nodes. This is all modeled off SCN, including 2 edge nodes that were actually running in SCN at the time. This gave us a mixture of node types, capabilities, and internet connections, because essentially we believe this is fundamentally going to be a heterogeneous network. And so we want to put that in the evaluation. We did 4 test scenarios. There was cloud versus edge and fiber versus cable with randomly sampled backup networks. We probably could have optimized the backup networks, again, for sort of performance reasons, and we think that's something that they would do. We compare this against a standalone cloud core. This is Open5GS on Azure. We picked Azure because it had the lowest latency to test nodes, but we want to note that dAuth in backup mode provides functionally new capabilities relative to a cloud core. So this is not an apples to apples comparison in that regard. You know, dAuth does more. And so that should be considered when thinking through the data. Okay, so first line of the data. This is 20 auths per minute, 8 backups with a threshold of 4. And what you see is kind of what you'd expect. At low load, the simpler cloud core is more performant, but not robust at the kind of failures that we're talking about, right? If the cloud core goes down, we just lose access and we lose roaming and all those sort of things. As we increase this up to 200, you see significant drop off from the cloud core. And these are where the scaling properties start to manifest. We actually get that nice backup behavior that we're looking for with the break even at around 100 auths per minute. And it's nice, these are both Open5GS, so it's a good apples-to-apples comparison in terms of the technology stack itself. Okay, so the last thing to think through here is that dAuth can run locally or in the cloud. And cloud instances are almost certainly going to have significant improvements in reliability than the kind of installations we're seeing with our partners. We have to support both as a project. This is because our partners prefer to run their own services for both autonomy and security reasons. However, this distinction between cloud or local deployments is actually fundamentally perpendicular to dAuth's design. The thing to think through here is that we're trying to support private networks, and private networks are foundationally independent. If they're running all of your traffic through a single private network, that's not a private network, that's an MNO. And so by having multiple private networks together and trying to federate them in the way that we are, it's going to be a distributed system. And distributed systems need to be fault tolerant. So here's a fault tolerance mechanism for that, even if the uptime goes up. As you run more nodes, even at a really good uptime, you're still going to have outages as long as you have enough nodes in the network. So, all right, thank you all so much. Feel free to reach out and chat with me or Matt about the project. We'll be around. Thank you.